and welcome to this new tutorial video. The calculation of electromagnetic force associated to a system of conductors can be very useful for safety purposes or for the mechanical design of electrical substation, in particular for the structural assessment of supports or post-insulator. The new features of XGSLab provide an excellent guidance and help in this respect, and they also enable easier and more thorough calculations than what the standards propose. In this video, I will show you the workflow to accomplish this. Before starting, I would like to share with you some basic information about electromagnetic forces. In fact, I want to recall that magnetic force is just a third or a part of Lorentz force, which is composed of two terms. The first one, known as Coulomb electric force, and the second one, which is the one of main concern and importance with respect to what is going on in this video, which is the Laplace magnetic force. Indeed, this part of Lorentz force is due to the interaction of charges in the conductors, specifically the conduction current, with the magnetic field produced by the current itself. In full conditions, we have some information that can be found in the standards. Indeed, we can say that magnetic force plays the main role when a substation undergoes a fault and we want to compute the forces due to this fault. And for this reason, standards mainly focus on this condition. The reference standards on this topic are mainly those three here, and more precisely, we can say we have the international standard, which has been traduced in the European standard, which is the first one. It is the IEC 60865 part 1, and we also have the part 2, which is which deals with some example calculation, which can be very useful. And then we have the US standard, which is the IEEE 605, which is a wide guide for bus design in air insulated substation, which contain a part related specifically to electromagnetic forces and effects evaluation, which, by the way, recall often what is exposed in the international standard itself. For this reason, in the continuation and in this tutorial, we will mainly focus in the standard only. The magnetic force, as treated or as proposed in the standard, is computed by assuming a three-phase or line-to-line fault only. And it is also assumed that we have three or two parallel conductors that are laying on the same plane. And it also considers that the conductors are indefinitely long in the sense or in the term that the distance is constant and is much smaller with respect to the conductor's length. Given these assumptions, it is possible to obtain this equation here, and with some specific term related to the peak value of the short circuit current, and this coefficient that depends on the short circuit type, determining whether we have a three-phase fault or just a line-to-line fault. And based on that, we have two possible values. In fact, the actual curve of the magnetic force during a fault, as exposed and described in the SIGRE 105, it's quite complicated and it's far from being completely sinusoidal. We mainly have three terms, a steady term and a decaying term, which are plotted here. So what is important to remember since now is that the computation performed in the code and in XGSLab just consider this term, so the steady term, which has a frequency equal to 2 times omega, and because mainly the standard proposes the formula, which is this one, so this one is carried on with this assumption, and then all the, let's say, non-perfectly sinusoidal term which might be decaying or steady, okay, so let's say this one and this one and this one are taken into account by means of the peak value of the short circuit current. If we now go back to the software interface, we can open our project and you will find a new tutorial specifically for the electromagnetic forces calculation in the setup. So I will open this file and I will describe the main steps. So as it usually happens with an XGSAFT project, you can set the waveform, then you can decide the soil model. Usually what I propose is to use a uniform model, since giving the conductors in the air mainly doesn't require a very precise description of the soil. So a uniform model, it's fair enough. Then you have, of course, to import your conductors, and here you can have your import interface, in which by linking the DXF file, you can select the layers. About this aspect, I want to show you here the DXF I have used, in which you can see the main busbar, which has been split in the different several parts accordingly to the layers, okay? And then you have the background, and in this case, some incoming lines. This substation example mainly deal with a producer bay here, which is conveying power to the grid, so the power flow will be more or less along this direction. So after we have imported our conductors, we can check the outcome of the import from the list of conductors. In this case, you may notice that we mainly had three groups of conductors: the L1 group, the L2 group, and the L3 group, which correspond in the DXF to the three phases of the system with a corresponding layer. So we have L3, so here we have L2 as layer, and L3 and L1, excuse me, and so on. Of course, we have respected this subdivision, this overall subdivision in the whole DXF to help us when we import, and to also help us when we have to set a source in each group of conductors. For instance, if we select the L1 group, we can then select all the conductors of this group and check the source. So the type is source, is not a victim, and here we can see that we have a voltage with respect to the ground source and a current. The current, you can guess it from the value. It's the RMS value of the short circuit current. In this case, is a typical three-phase short circuit. By doing this, you can simulate theoretically any situation, also something which is coming, for instance, from a network analysis, or from a power flow, from a short circuit simulation of another software, or of nets, for instance. So you can assign to each branch of the substation, in this case, the value you want. And based on this, you can then see if everything is correct in terms of inserted value. And by pressing debug, we can proceed, as it usually happens, toward the calculation or the computation. Another paramount aspect to be remarked is the discretization step or fragmentation level of the conductors. Indeed, you can see here the main conductors in which the substation is subdivided. And if we zoom in, you may now notice the quite dense step, given the arrows, of the fragmentation. This aspect is very important when dealing with forces, because as a next step that we will see in a while, you have always to remember that the resultant force and each component of the resultant force is applied or calculated to each element barycenter. So the more you subdivide or discretize your conductors, the more discretization and description of the force variation you get. And since this force, as you can see from the plot, oscillates over time with a frequency which is the double of the main frequency of the system, it's important, if you want to capture the small variation, which are the main reason for which you are using this new tool of the software. I'm now back to the 3D debug visualization, and I would like to focus your attention into the 3D, let's say, description in the space of the conductors. Indeed, as you can guess, here we have an overhead line, and here we have some rigid busbar bay. Okay, this one is for the collection of the bays, and this one is that one that is going towards the transformer. If we go now back to the list, we can see that this aspect is let's say, confirmed by the fact that we have been using some overhead line and overhead line type conductors and some pipe type conductor, which are, of course, which can be found also for the L2 and so on. If we go to we go and check the conductors library, and we look for those two, which are this one, which I also can filter. Okay, you can see that we are dealing with pipe type conductor, so tubular with no covering, and with this, it's aluminium, so they are made of aluminium, and they are characterized by those two external diameters. At this point, we can conclude this preparatory part. Everything it's set. We have our sources, we have our conductors, we have chosen when importing, as it usually happens in XGSA, the conductor types and so on. And so we can compute and launch the computation. The computation is now finished, and I would like you to notice that it just took some seconds due to the fact that we are dealing with sources in a uniform soil model. Now it's the time of actually computing the forces, and this will be, if the model is set correctly, it will be extremely easy. Before doing that, sometimes it might be useful going to the let's let's say, classic result tab and check for the current and the voltages you have set. For instance, if we check the imaginary part of the current, we can see that we have the three phases correctly connected. So each connected component, let's say, is current one to the other, and also the values are corresponding to what it should be. The same happened, for instance, with potential. So if we go here, we will obtain the same color subdivision with, of course, different values, which have to be corresponding to the source we have chosen in advance. So we are now in a situation in which we have our solution, we have checked it, and we concluded that it's current back to our expectations. So we can now go to distribution of the EM force, and finally we can calculate just pressing the button. Everything is automatic. You can decide the sampling number in a period of the sinusoidal wave. This is due to the fact that the force is instantaneous, and you can find more information about this in the user guide. But just consider that what it will be displayed is just the maximum values of the instantaneous force. So what it is done inside the code is a sampling of the sinusoidal wave with a given step. Here we have three possible choices. The default, if you don't even insert anything, is 1000. So here we will confirm this, and we can just calculate. Also in this case, the it's very, very. We now get rid of the main confusion of the plot, and we go back to the EM force distributions plot. Here we have the exactly the same interface as for results, and by filtering and seeing the maximum, the median, and setting some limits, you can decide the component you want to display, and you can decide if you want a 2D visualization or a 3D visualization. You can see that the force in this case it's quite uniform. As a first, let's say, as a first impression, it's quite uniform, and it is just changing in the corner, let's say. But for instance, if we filter one of the conductor and we see which one we have selected, which is this one, we can then plot as a view 2D, and we can see that with more sort of focus, the difference is not that negligible with respect to the inner part and the outer part of the conductors. Eventually, you can also export the values using the CSV export. The export is based on what you are seeing on your representation of the distribution. So in this case, if we press here and we write something, for instance, L2, we can see the format of the file, and you can see that you have the descriptions of the linear plot with all the values plotted with the measurement unit. For instance, we want to save. If I go back here and I press the same button and I override this one, the result will be slightly different in the sense that you can also see the 3D position. Let's say, just pay attention to the fact that the z-axis is downward, let's say, so -7 means out of the ground. and you will have the same four components, but you also have the positioning on the body center of the elements of the fragmentation I was discussing before. So, for instance, this is very useful if you just want to launch the calculation and computation of the forces in XGSA, and then you want to export the values of the forces obtained to, for instance, build your own finite element mechanical model for the vibrations or other purposes that might be interesting to you. We are now practically done with the computation of the forces. So I would just like to recap the main points we have seen and on which I would like you to focus your attention when setting this type of project. So as main tips, let's say recap, it's important to prepare the DXF in a smart way and to group the conductors such that you can quickly filter them because given some tags, and if the tags are set correctly since the beginning, this will help you during all the operation you want to perform in the software. When using sources to compute the force, it's mandatory to set both currents and voltages. Otherwise, the classic computation will not have any trouble, but the force calculation will fail. It is also possible to use victims instead of sources, depending on what you want to model and on the behavior you want to reproduce in the software, as we have seen before. About the conductors types, all the types are available, so you can use rigid or flexible pipe type, screened conductors, and lines type too. So you have the maximum flexibility in this respect. Just it is important to use it wisely. It's very important to use a proper fragmentation of the conductors if you want to capture the force variations. Otherwise, you will just see a single value for a very long conductor, which will be, of course, averaged along the whole conductor, and this will make your calculation less meaningful, let's say, and less useful too. As a final remark and tip, let's say, it's very important before launching the force, especially the very first time, to pay attention that the voltage and source result you have obtained based on the source you have set, it's current with your expectation, at least within a certain level, of course. This second part is about the electromechanical effects evaluations. Indeed, as exposed in the standard reported in slide, we have three main aspects when dealing with the mechanical effects evaluation: the computation of the electromagnetic force, the calculation of the force effects in case of rigid conductors, and the same type of calculation when considering flexible conductors. This is describing the phenomenon in which during a fault electromagnetic forces arises, and so some stresses and loads have to be taken into consideration when designing our mechanical structure. So the first ingredient is the electromagnetic force, and then based on the type of the conductor, one can apply the EMF effects for rigid conductors approach of the standard, or the one for the flexible one. In the software, only the approach for the rigid conductors has been implemented and will be the focus of the continuation. So the mechanical effects according to the standard can be computed by traducing the forces on the rigid conductors into stresses and loads. This is done by using some formula that can take into account both the static and the dynamic effects. In fact, by consulting, for instance, the SIGRE 105, it is very important to always keep in mind that the dynamic effects have an important impact on the final outcome of the calculation. Indeed, depending on the ratio between the natural frequency of the mechanical structure and the electromagnetic frequency, typically 50 or 60 Hz of the source or fault current, one can obtain an increase or a decrease of the overall effect when focusing on the dynamic aspects. For this reason, following the approach of the standard is very important if one wants to keep things quite simple and general. On the other hand, if one wants to accurately compute dynamic effects, it is necessary to resort to some finite element analysis, which has to be carried out for some predetermined configurations on a specific design and layout. Since we want a general tool, the approach used in the software is based on the standard as far as the stresses and loads are concerned. We can start again from the software and we can open the same tutorial you can find in the setup. And now we will focus on the effects. So the project is now open. We can close the page and we will just use this button to access to the tools EMFX evaluation. Before doing that, we have to set a standard for the electromagnetic effects. And in this case, it has already been done. So we now open this, and you can see here that the tool is available and you can interact with it. First of all, you have to choose or set a description. This menu allows you to load some predetermined data or some previous calculation you have already performed. This combo works in a way that whenever you enter a new description that is not present in the list, and then you launch the calculation after entering all the required data, then a new description will be saved and will be available in the list. In this case, we can enter a new description to start, let's say, a new calculation. Here you have the frequency, which can be set or can be automatically detected in case some frequency has been set in the waveform tab here. And then you can notice that the import results section is disabled. This is due to the fact that if you go to distribution, there is no an available computation here. And so this is the reason for which you cannot import any results. Keep in mind that at the moment, the electromagnetic force calculation is not saved inside the project due to the fact that it's quite an instantaneous calculation. It's an instantaneous post-process. So every time you reopen the project, you will have to recompute the electromagnetic force if you are interested in that. In this case, we have opened the project and we have not already computed again the force. So the tool is based on the standalone mode. In the standalone mode, you can directly go to the local calculation area. You can select the short circuit type and then enter the short circuit current. In this case, we will use the RMS value as seen before during the electromagnetic force calculation. Then you have to set the main conductor's distance. In this case, I will set 2.2 meters. I'll tell you why later. And here you can see the per unit length due or calculated based on these three values. Here you can decide whether to import the force or use the locally calculated one. And in this case, since no import force is available, we will just rely on the local calculation. Then you have some correction factors that have to be set accordingly to the standard prescription. All these parts, or all the missing yellow boxes, are thoroughly described in the user guide, in the tutorial PDF, and also, of course, in the standard. So I will go through them quite quickly. I will set, for instance, this value, which will give me this peak factor. And this peak factor is the one I've shown in the beginning of the tutorial, related to the non-steady state part of the short circuit current that traduces into an increase of the electromagnetic force effects. Then we have to select mechanical data. This is a new part of the software and is linked to a new library, which can be seen here. This new library provides you a set of busbar, which can be set and tweaked, let's say, in advance and offline in any moment, and then saved, as you can done with any other library of the code. In this case, we will use two circular shape rigid conductor. Here you have just rigid conductor. You don't have any flexible conductor because the calculation of the EM effects for flexible conductor is not available at the moment, and so the group is just reached, but it will be extended in future. And here you have the same values. In this case, you can find in the conductors list. If we now filter this again, and we can filter this one too in the same way. This. And so you have, for instance, the same outer diameter and the same section with some extra items or data. All these items are explained from the mechanical point of view in the standard, and also for this aspect, I will not go thoroughly through them. It's important to remember that there is no automatic detection of between the mechanical data library and the conductors library, in terms that even if physically the conductor is the same and has some electrical properties that are described here and some other mechanical properties that are described here, the code doesn't link the two automatically, because, for instance, if I consider all the conductors, you can, and when dealing with the mechanical aspect, use also rectangular shape, solid or pipe bars. This is not possible as a conductors, but can be in any case based by following the standard prescription. And you can find more detail about this in the user guide. What you have to always remember is that you have autonomously and independently decide which type of mechanical data you want to link and to use in this case. Then you have to decide the span type, which is also this one, a parameter that can be found in the standard. And finally, you have to set the distance between the subwords. Once you are done, you can just then decide whether to apply the dead load of the bar and then calculate. You will see all the output data here and also ideal, let's say, representation of what's going on in terms of loads on the two subwords. Here you have the natural frequency. You have, for instance, some tip about the possibility to use dampers and all the stresses involved in the structure. There is the outcome of the withstanding of the short circuit here, and then you have all the loads that are decomposed accordingly to the two main directions of this 2D representation of the conductor section. The standalone mode computation is practically finished. You can now export your results. Here we have the previous CSV. This will be EMF. Local, so better standalone mode. We can save the CSV, and you will see in a while that all computation data available is recorded in the exported CSV. As the final part, you can see that the computation has been added to the list. This means that if I close everything and then I go back to the tool, I will find my calculation and I can launch it again by pressing this and obtain the same result. I'm now going to show you the second way in which the tool can be used. In my opinion, the more interesting one. We are still in the tool, inside the tool is open, and we have input results here, which is disabled. If we go back to analysis and we go to this distribution and we calculate forces, some result. For instance, this one. I will now close it. Nothing has changed. I have to reopen the tool, and in this case, the input result is now active. How does it work? Basically, it's more or less the same of the distributions block. So you can click on it and select, for instance, this point. Automatically, the tool understands which is the conductor, the tag, the number of the conductor, and the average current, which hopefully will be consequent to what you have set as a source if you are using sources. Then, based on the support direction, on which I will come back in a while, there is a decomposition in the 3D space, or better, from the 3D space to the 2D section of the conductor. And that's where the support direction intervenes. What does that mean? It means that here we are in the 3D space. Theoretically and also actually, we will have some supports will be placed starting from the ground or differently on a wall. Sometimes that happens too. So you have to describe the direction of one of the two supports. It's not important that direction is perfectly the one you have in your substation or in the reality. it has to be something almost parallel to that. So if it's, for instance, everything, as in this case, is supporting the starting from the ground, the support direction will be this one, 0, 0, 1, which is the Z direction. And so we will have something which is stick in the ground. Based on that, and based on the 3D geometrical description of the conductors, there is a decomposition, an extra decomposition of the two forces. In this case, you will see that the decomposition it's almost normal to the support, and so is acting in this direction here. You don't have any, let's say, appreciable components directed parallel to the support, at least for the conductors I have selected. If I now go back and I choose this one, for instance, things are changing. We, of course, have a main component, which is still normal, but we also have a parallel component, which is parallel to the support. And this is the reason for which one have to import the outcome of the electromagnetic force calculation obtained with the XGSLab software. This is very beneficial, especially when you have complicated geometry, as in this case. Of course, if you have some parallel bus bar, as in this part, the result will not be so different from the standard prescription. Differently, if and when things become trickier, there might be quite large discrepancies. At this point, some comparison is very useful. And that's why the local calculation area is always active and available. In this case, the main conductor's distance is 2.2 meters. So this means that the distance between the phases is 2.2 meters. By entering this data and by considering a three-phase short circuit, which in the XGSLab calculation has been simulated by impressing some current sources in our conductor accordingly to a three-phase fault situation, we obtain this value. This value can then be compared against the actual value obtained in each part of the conductor. In this case, you can see that the difference is quite small. In other case, it might be very, very, very important, as in this case. This case shows that the parallel component is larger than the normal component because we were clicking on the end side or the end parts of the bus bar, in which this strange arrangement will for sure have some consequences. And this immediately gives you an idea of where to focus your attention, and can be done also in advance with respect to the EMFX calculation by using also, for instance, the show vectors mode, which is this one, which can be tweaked accordingly to our purpose. For instance, if we are interested there, we can just filter this one, and you can see that in the end point or end side part, things are not as the standard prescribed. At this point, it's also important to keep in mind that these values are obtained as an average of the forces, electromagnetic forces on the elements along a single conductor. And this, let's say, reflect and has an important link with the description or the model realization. If we zoom here, we can see that from here to there, we have a separation of the actual busbar due to clamps that can be moving or fixed and so on. So when building the model, the DXF file, with the final goal of computing the EM effects, one have to possibly take this into consideration and split the conductors in, let's say, subparts in which every conductor is separated one from the other with respect to the actual mechanical separation. By doing this, you can then perform your average in this side or that side and decide whether use one of the other value. Once you have decided in which part of the busbar system to focus your attention and which span you are modeling, you can just select, for instance, import results. Then you have to compile all the other independent data that are indeed independent to the fact of importing or locally compute the force, and then you can press calculate and obtain your result. For instance, we will use hopefully that I will use to span again, and then we have subburst distance, which for instance might be always 6 meters. We'll apply the dead load, and you can see here that on the contrary of what you would have obtained by using the local calculation, an important influence of the force component, which is parallel to the busbar. This is a result that cannot be predicted by using the standard, for instance. In fact, if we go back and we switch to local calculation and then we press calculate, the numbers and the direction of the force is quite different. Also, pay attention, for instance, to the fact that if I'm, for instance, wait, here, and I'm just considering all of them, and I go to view 3D, and for instance, I am starting the design of this corner, which is it's quite far from being a standard solution as for busbar arrangement. I mean, from the mechanical point of view, it's something which is common, but is not strictly superposed to the configuration, the ideal configuration of the IEIC standard. So in this case, theoretically, what the standard tells you is that the maximum force is in the central conductor. But if you click on that, remember this number, it is not going like that. It's slightly higher. And top of that, this is longer. So you have a longer conductor with a almost equal or even in this case higher value of force. And so this might be the bounding, let's say, conductor from the mechanical stresses and load point of view, not the inner one. And this is just one example out of a million. So as a conclusion, once we have decided which part we want to investigate, now I will just upload some previous results. We can calculate with the import results option and obtain our file, our result. We can then export and obtain now a new file, which will be, for instance, same as before. but with import option, and the file will be quite similar to the previous case, with the specification here that the results of the EM force have been imported from the software. So just to conclude, we have seen that two modes for the tool are available, a standalone and an import mode. That the description combo box label helps to store previous calculations. You can then re-upload them and you can modify some of the items or parameters if that is the case. Another important aspect is that the way in which one subdivides the conductors in the big set reflects into the results of the normal and parallel decomposition of the force when you are using the import mode solution. The choice has thus to be current with the actual clamps placing and the substation in your layout, and so it has to reflect the final configuration of the mechanical busbar. The support direction describes the direction of your support. This doesn't mean that you have to be exactly reporting, that you don't have to exactly report which is the, let's say, the direction of your support, but you have to determine whether your support are, for instance, stick into the ground or fit on a wall, and based on that, inserting the right numbers. You have to use a proper fragmentation of the conductors if the actual force variation has to be captured. And also you can resort to the CSV export, and you can then merge and collect all of your calculation in a unique XLSX file, so an Excel spreadsheet. And finally, one has to consider that the input dataset and the model on which we have been working during this tutorial to compute the forces and thus the effect can be the same, and it is usually and often the same, in which one can compute the electromagnetic fields and the interference. And so this leads to quite saving in terms of time for your design.